Hi everyone, I'm Catherine Sanchna, a PhD scholar from IIT Madras. I'm one of the TAs of this course, Mechanical Characterization of Bituminous Materials. This is a tutorial session which happens every Tuesday between 6 pm and 8 pm. This session will be recorded and also posted on my YouTube channel, the link for which will be provided by the NPTEL team. If you have any queries, please um, post it as a comment below the YouTube video, or you can ask in the discussion forum in the NPTEL website. So without any further delay, we will begin with today's session. So I will share my screen. Yeah. Okay. So this week, last week, we would have seen Nivita ma'am's lectures mostly on uh, the chemical composition of bitumen. So in this week, we will be seeing a few more lectures on the chemical composition of bitumen along with aging of bitumen. So yeah. So let us first skim through these questions. Okay, not skim through them. We will go. These questions are in a random order. We will go in an order in which man has given the lecture. So first we will finish questions on the chemical composition of bitumen. Then we will proceed to aging. And in aging also we will proceed in a sequential manner, as in we'll first proceed with reversible aging, then irreversible aging, and then so on. So let us first, in this week, ma'am would have discussed about, in chemical composition, alright, ma'am would have discussed about functionalities, morphology, right, and molecular composition. Right? So, yeah. So, and then she would have gone to, she would have also discussed relating chemical composition with physical or rheological properties. And after this, she would have started with aging, like what is aging, what are the types of aging, reversible, irreversible, right? Laboratory, I'm not writing it in a sequential manner as ma'am has taken. Okay, laboratory simulation of aging, and then factors influencing aging. Okay, and a few more topics. So First, we will finish questions on which have questions which are related to chemical composition. So first, we will begin with the questions. Okay. So the first one is about aging. So all these are about aging. Okay. This question is on chemical composition. So let us begin with this question. So pick the correct statement regarding the thermal events seen in bitumen through a DSE test. Right? Just a second. Yeah. So, sorry about that. So, DSC is the abbreviation of differential scanning calorimetry. Okay. So, yeah. This differential scanning calorimetry is used to identify the thermal events in bitumen. Okay. Now, okay, let us see a few thermal events. What do I mean by thermal event? The like observing the heat flow, okay, in a sample, okay, with changes in temperature. So let us take a sample, and if you heat it or cool it, there will be some thermal events happening in the material. So what do I mean by thermal events? It could be melting. Okay, so for example, let us take ice and let us subject it to some heat. Okay, you will observe that the ice starts to melt, right? That is a thermal event. Capturing that thermal event through heat flow, so now you know that you can visually see that your ice is melting, but how will you capture it? So for that, we are using a technique called differential scanning calorimetry, where we subject the material to the heat. So we make a plot of temperature, okay, in the x-axis, and heat flow, okay, in the y-axis. Now when you are able to so by identifying certain phenomena, okay, or by identifying certain changes in this graph, you will be able to see if your sample is you will be able to say if your sample is melting or undergoing crystallization, or if it is having a glass transition. Okay, so for that we use this differential scanning calorimetry. So now, what are the few thermal events? It could be melting, it could be crystallization, it could be glass transition, okay, there are few other thermal events also, but we for now we'll just stick to these three. Okay. So now this DAC is used to capture the molecular arrangement in bitumen. So what phenomena or what um, so what can what is the terminology to understand the molecular arrangement of any material? We say that if the molecules are arranged in a well-defined fashion, well-defined molecular arrangement, okay, we call that material to be crystalline. Okay, and if it does not have a well-defined molecular arrangement, we will call it as amorphous. Right? So when you do this DSC, you will be able to see if your material um, uh, if your material has crystalline components in it or amorphous components in it, and even if it has crystalline components, at what temperature it starts to melt. If it has amorphous components, at what temperature it undergoes glass transition. Now if you see me, if you notice me clearly, I would have said melting for crystalline substances and glass transition for amorphous substances. Why do I say this way? Why can't I say that amorphous substance starts to melt or crystalline substance has a glass transition temperature? Yeah, it is because crystalline substances will have sharp melting points. Okay, say your ice has a melting point of 100 degrees Celsius. Your ice has a freezing point or crystallization point of 0 degrees Celsius, right? Whereas your glass transition temperature, you cannot associate a single temperature at which it starts to melt. It melts, okay? It will melt over a range of temperatures. Okay, so that is why, so when the melting, capturing the melting or solid to fluid transition, like melting is the transition from solid state to fluid state, right? Sorry, melting at 0 degrees Celsius. I'm sorry, I would have said melting at 100. Sorry, that is boiling, right? So melting at 0 degrees Celsius, right? So it transfers from a solid state to a fluid state, okay, when you start heating it above 0 degrees Celsius. Similarly, for a glass transition temperature, of amorphous substance, you cannot associate a single temperature to it. It will start melting over a range of temperatures. Okay, that is why we call that the transition from a fluid state to a solid state or solid state to a fluid state in the case of amorphous substances as glass transition temperatures, and in the case of crystalline substances, the transition from fluid to solid or solid to liquid state, we call it as melting or freezing. Okay, so this glass transition temperature, okay, it is for amorphous substances. Now, how will you understand from the DAC curve if your substance is undergoing melting, or if it is crystallizing, or if it is undergoing a glass transition? Now, for bitumen, for example, if you take bitumen, you don't know the components that are present in it, right? You have a hypothesis of this could be the possible components present in bitumen, but you may not know what exactly is present in bitumen. That can be captured by this glass transition, by this DAC technique. Now, if you see, this is the heat flow curve. Okay, so how do they actually measure this heat flow? What do they do is, they will have two pans, okay, one with the sample and one an empty pan. Okay, either it could be an empty pan or it could be a sample with a reference or a reference sample. Okay, so what do? They heat both the pans. Okay, now they heat it in such a way that the temperature in each of the pans get increased in a linear fashion. Okay, they will have a constant rate of heating, constant increase in temperature. Now, to reach this temperature, to reach a particular temperature, it some sort of energy has to be provided, right? A heat energy has to be provided. So this heat energy that needs to be provided for a sample, for the sample with the pan, and for the sample without the pan will not be the same. Why? Because this sample will undergo certain thermal events. Say it will undergo melting. In such cases, what it will do? Or crystallization. So whenever it undergoes a transition from one state to another, it it requires more heat. It requires more energy to do that. So in that case, the heat energy, it either needs more energy or it needs lesser energy depending on the thermal event that it is undergoing, right? So in that case, the heat energy that needs to be supplied to this sample either will not be constant, right? Because it depends on the sample and the thermal event it undergoes. So, um, so the heat energy is going to be different. Now, if you see the heat flow curve versus temperature, let us say that my upward direction points to endo. In that case, this heat flow curve, if it has a sharp point in the endothermic region, okay, you know that in endothermic reaction heat is lost, right? Heat is heat is absorbed, heat is taken in. In exothermic reaction, heat is given out, right? So if an endothermic reaction happens, if there's a peak in the endothermic direction, you know that melting is an endothermic reaction. So you can say that at this particular temperature, this sample undergoes melting. Also, this presence of melting point or this peak, okay, tells that my material is a crystalline material if it has only this peak. Okay. But our bitumen will have a combination of crystalline and amorphous substances. We saw the Sara fractions in bitumen, okay, where the crystalline fractions are associated with the saturates, which are mostly N-alkanes, okay, and the amorphous components are due to the aromatics in bitumen, right? So it will have a combination of both crystalline and amorphous. So it is a combination of both crystalline and amorphous substances, which means it needs to have a peak at some temperature to indicate the presence of crystalline substances in it, and also it should have the presence of glass transition temperature to indicate amorphous components in it. So now I told you the presence of this peak, okay, indicates melting, and it shows the presence of crystalline substances. Now, how will I identify glass transition temperature? How will I identify glass transition events? So what will happen is, this heat flow curve will actually be a straight line, and at the point of glass transition, so this they call it as the baseline, okay. After it undergoes glass transition, there will be a shift in the baseline. So the baseline will get shifted, okay, and this point is identified as my TG. Okay, they will just take the inflection point as the TG, the point of intersection of these two slopes, as the glass transition temperature. So besides this crystallization, melting or glass transition, based on how the heat flow curve varies, many people have identified many thermal events, but for bitumen we are focusing only on these three thermal events. Okay, if you see, there is one more advanced technique, okay, more advanced than DSC, called MDSC, a modified or modulated differential scanning calorimetry technique. In that case, okay, so if when they did this on bitumen, they were able to identify a few other thermal events. Okay, a few other thermal events. They were able to identify two endothermal peaks, two melting peaks, two crystallization peaks, like that. Okay, so it was able to give a lot more additional information than a normal DSC. So for now, let us simply understand that crystalline a melting peak indicates the presence of crystalline fraction, and a glass transition indicates the presence of amorphous fraction. Okay, and the corresponding temperature refers to glass transition temperature. Now, in addition to that, okay, you should also know that there is some other advanced technique called MDSC, which can be able, which will help you to understand this material better. Okay. So, yeah. Now coming back to this question. Pick the correct statement regarding thermal events seen in bitumen through a DSC test. So, the melting peaks are attributed to the crystalline fraction and bitumen. Did we see this? Yes, right? The melting peaks, crystalline fractions. The glass transition is attributed to the crystalline fraction and bitumen. Is glass transition attributed to crystalline fraction? No. It is attributed to the amorphous fraction and bitumen. The melting peaks are attributed to the amorphous fraction in bitumen. No, they are attributed to the crystalline fraction in bitumen, and the crystalline peak is attributed to the amorphous fraction in bitumen. Right? Crystalline peak is for a crystalline material. So, obviously, these three are not the correct options. Okay. Now, again, coming back to the chemical composition, and one of the techniques to identify functional groups will be FTIR spectroscopy. Okay, before even realizing, I told the answer. Okay. Sorry for that. For elements, we saw last week how what technique was used to identify the elements present in bitumen, and also technique to identify the molecular weight in bitumen, of the molecular weight distribution of bitumen, right? Here, FTIR is used to identify the functional groups in bitumen. Okay? Like ma'am said, so how does this actually work? So, the bitumen with functional groups, okay, each functional group, depending upon the number of bonds and the atoms in the functional group, okay, they will start vibrating at a frequency. So they have their own frequency, right? Every material has its own natural frequency. And now you know the concept of resonance, right? When you pass a frequency which is exactly equal to the natural frequency of a body, then by the concept of resonance, these two, so the body which has the natural frequency will oscillate more. Okay, its amplitude magnifies. Okay, so that concept is used in this FTIR spectroscopy. So what actually happens? All these functional groups will have natural frequency, and when you pass frequency spectrum, okay, a spectrum of different frequencies, okay, what will happen? the functional groups will absorb the frequencies which is equal to the natural frequency, their natural frequency, and remit the remaining frequencies. So now, based on, if you make a plot of the inverse of frequency, which is wave number, to the absorbance, you will be able to identify a few peaks depending upon the functional groups present in bitumen. These peaks tell you that at this particular wave number, okay, so each material or each functional group, be it where it is present, it will oscillate, or it will resonate only in its own natural frequency, right? So it is like a fingerprint. So at this particular wave number, only this functional group will show its peak in an FTIR spectroscopy. So like that, depending upon the wave number at which this peak occurs, this technique can be used to identify the functional groups in bitumen. So that is why the FTIR spectroscopy is used for. Okay, the full form of this stands for Fourier transform infrared spectroscopy. Okay, so the answer to this is, functional groups. Okay. The third is also is from the chemical composition. So fluorescence microscopy has been successful to highlight the morphology of water. So as you had you listened to ma'am's lectures, she would have said that bitumen, being an opaque material, okay, it cannot be studied under a regular microscope. Okay, so or optical microscope, and there are a very few techniques, but they were able to identify a very few techniques which could be used to study the morphology of bitumen. And one such technique is fluorescence microscopy. So what this will do is, if your material has fluorescent particles in it, okay, fluorescent particles in it, sorry for the poor handwriting, if your material has fluorescent particles in it, then it can be captured in a fluorescence microscopy. Now, if an ordinary bitumen does not have any fluorescent particles, so that cannot be captured by a fluorescence microscope. Only if your material has fluorescent particles, it can be captured, right? And if you see, only SBS modified bitumen, which we call it as the elastomer, can be captured by can be studied under a fluorescence microscope, because only the SBS particles are fluorescent. Okay, if you see elastomer, both of these are modified bitumen. What do I mean by modified bitumen? I'm adding some modifier to it, okay, some modifier to my bitumen to enhance its properties. Okay, what properties, or how are we adding, in what dosage we are adding, all that will be explained by ma'am when she teaches polymer modified bitumen. So if you see, both of these are modifiers that have been added to bitumen, but not all of them, like both of them cannot be, not that a modified bitumen can be studied under a fluorescence microscope and an unmodified cannot be studied. It's not that case. A plastomer is not a fluorescent particle, but an elastomer, which SBS stands for styrene butadiene styrene. Okay, so this is a fluorescent particle, and hence it can be studied under a fluorescence microscope. So the answer to this is SBS modified bitumen. Okay. Okay. These two talk about the models that have been used to represent bitumen. So all this while we were seeing some techniques to identify um, or some techniques to capture each and every component of like a part of bitumen. Say one technique was used to capture the elements in bitumen, one technique was used to capture the molecular weight of bitumen, the other is used to capture the functionalities in bitumen. Right here, they they want to understand how uh, um, how these particles or the fractions that we saw something called as Sara fractions, right? Um, when we try to study bitumen using the fractionation technique. Now they wanted to understand how these fractions are arranged in bitumen, or how to model this bitumen. Why to model this bitumen? So that when you try to associate this material with a model, you will be able to maybe try to reason out why this material behaves in a particular way when subjected to this kind of load or this temperature. Okay, so in order to do that, they try to associate this material to a model, and the most commonly used or most popular model used for bitumen is a colloidal model. So what is a colloidal model? You know what a colloid is, right? It will have a dispersed phase and it will have a continuous phase. Okay, it will have some particles dispersed in a fluid. Okay, so that is what a colloid means. Now what this colloidal model assumes is these colloidal particles contribute to the asphaltenes. Okay, we saw this in the Sara fractions. This A stands for asphaltenes, right? And the continuous phase is occupied by maltenes, which are these three components. Okay, so these asphaltenes, okay, this dispersed phase, they call it as micelles, okay, or micelles. Now there are a few modifications to this colloidal model. Okay, so an improved version or the next version of colloidal model was, or uh, the next evolution of colloidal model. Okay, it said that this asphaltenes form the core of the micelles. Surrounding that you have the resins. Surrounding that you have the aromatics. Okay, and later you have the saturates. It's not exactly surrounded, but as you go far away from these asphaltenes, you have particles which are of decreasing molecular weight. Okay, and it is hard to uh, demarcate the point where this micelles end and where this continuous phase starts. Okay, so that is one of the evolutions of the colloidal model. There are a lot more evolutions as well. Okay, so if you see, as per what I explained, okay, in the colloidal model, which among the following is true? The micelles are dispersed in maltenes. Is it true? Yes. Let us see the other options as well. The maltenes are dispersed in micelles. No. Maltenes are the continuous phase and micelles is the dispersed phase. So maltenes cannot be dispersed in micelles. It is the other way around. So now the third option, which is the lower molecular weight compounds form the core of micelles. What did we see here? The core of the micelles is occupied by asphaltenes, which are higher molecular weight compounds. So the third option is wrong. And the higher molecular weight constituents form the median. So surrounding the missiles is the medium, right? And we saw that as you go far away from the missiles or the core of the missiles, the molecular weight keeps on decreasing, and so the molecular weight of the medium is a constituents with lower molecular weight. Okay, so the answer to this is missiles are dispersed in multines. So let us see the next question, which is interactions among different constituents in the colloidal model is considered in what? So if you see, man would have explained different models, the Lenston model, Pfeffer and Saal model, SHRP model, all of the above. And of all the three models, the one model which considers the interactions among the different constituents is the SHRP model. Okay, so the answer to this is the third option. Okay, so this is a question which relates chemical composition with the rheological properties, or which, yeah, something close to that. So we'll see this question also now. Just a second. Okay. To obtain identical rheological properties from two bitumen samples, it is essential that, okay, for two bitumen samples to have identical rheological properties, what could be the rheological properties? It could be anything. It could be viscosity, it could be uh, complex, like absolute shear modulus, it could be storage modulus, it could be loss modulus, whatever. Okay, to have identical, it could even be penetration. Okay, as simple as that. Though you can, uh, though uh, they are just theory, or sorry, though they don't have any mechanics background to it. Okay, though they are just um, what to say, empirical measures, penetration or softening point. At this point we can also consider them, okay, as rheological properties. Now, to obtain identical rheological properties between two bitumen samples, it is essential that what? Okay. So what are the Corbett fractions? We know that Sara fractions are the Corbett fractions. If both of these have identical Corbett fractions, do you expect them to have identical rheological properties? If you see, ma'am would have said that just by looking at the Corbett fractions, though both the bitumen, let us consider this as A and B, though both A and B have similar Corbett fractions, they will not, need not have identical rheological properties, because despite the proportion that they are present in the bitumen, the interactions between them also play a critical role, a very critical role. So, though Corbett fractions are identical, their rheological properties need not be identical, right? Next option, bitumen samples are obtained from identical processing methodology. When we saw the extraction method itself, I would have said two bitumen of same grade, okay, if they are not from the same source, crude source is different, or if they are produced using different processing techniques, then they need not have identical rheological properties. So how will I identify Vg30 bitumen? It is identified as per IS 73, right? And what do I mean by so here by rheological properties they are considering only rheological properties, not consistency measures like penetration, softening point. Okay. Had they considered that, then um, okay, yeah, had they considered that, then they wouldn't have said um, sorry, why did I say this now? Just a second. Okay, let's go by this. Okay, let us say two bitumen which have identical, which have been identified as VG30 as per IS 73, as per all the measures, say viscosity, penetration, softening point, and whatnot, ductility. Okay, by using the table, you have identified two bitumen as VG30 bitumen. But if their crude source is different, or if the processing technique is different, then their rheological properties need not be the need not be the same. Now, if you see, they have said that they have identical processing methodology. One thing that they did not give you, just because they said identical processing methodology, you cannot simply jump and say, because this is so this option is like this option has been removed for you, right? Because it does not have a different processing technology or processing methodology technique, right? Just because they said that it has identical, they both have identical processing methodology, they need not have identical rheological properties, because here they did not tell you from this identical processing methodology did they um, produce a VG20 bitumen or a VG13 bitumen. By processing technology, I meant only the methodology, okay, like be it air blown or blended, okay. If they, even if they've used the same recipe, okay, these bitumen samples could have been from different crude sources, right? Which means they need not have identical rheological properties. Okay, even if they have identical processing methodology, they haven't told you what is their crude source. Okay. In that case, you cannot simply jump ahead and say that they they will have identical rheological properties. It need not be. Okay, so the answer to this is vague. So you cannot choose this option unless and until you have a clarity of, you have a clear information of all the possible factors that could affect the rheological properties of bitumen. The third option is they fall under same grade as per IS 73. Same thing, I told you, right? You classify two bitumen as VG30. Even then, which means what? Your viscosity, penetration, softening point, they need not be the same, but it satisfies the VG30 criteria. Even then, you cannot say that their rheological properties are same, for the very two reasons that I told here. One is the crude source could be different. Second is they could have had different processing technology. You don't know. So in that case, this also you cannot choose. So the fourth option, which is none of the above, is the correct answer for this question. Okay. So here, this question is also related to rheological property. Okay, based on the changes in temperature. Okay, So the viscoelastic solid to fluid transition refers to the transition in the response from water. The name itself says, right? Viscoelastic solid, fluid. So the transition is from viscoelastic solid to viscoelastic fluid state. Now, how to identify whether the material is in a viscoelastic solid state or a viscoelastic fluid state? There are many criteria, have been identified, okay, to capture this transition. It could be tan delta, okay. What is tan delta? It is G double prime by G prime, okay. If this is greater than 1, then it could be viscoelastic fluid. If it is less than 1, it is viscoelastic solid. Why do I say like that? Here my G double prime, which is the loss component, if it is greater than the storage component, then my fluid characteristics dominate, right? So it is a viscoelastic fluid. If it is less than 1, then my solid storage component dominates, okay. So it is close to a viscoelastic solid. Not only this criteria, there are many criteria, okay, which have been identified, okay, in literature to capture this viscoelastic solid to viscoelastic fluid transition, okay. So all this comes under aging. Okay, not this. Yeah. So the remaining questions are about aging. So we will talk about aging now. Okay, just a second. Yeah. The following are two compounds that are formed in high concentrations in the initial stages of aging. So what are the compounds that are formed on aging? What are the compounds that have been identified, or what are the functionalities? Let me call it as functionalities. On aging, it is ketones, carboxylic acid, anhydrides and sulfoxyls. Out of these three are compounds which are freshly formed on aging, okay, which are not present in bitumen as such. But after aging, they were able to identify these functionalities in bitumen. But this carboxylic acid they were able to capture this compound or functionality both before and after aging. Okay, so this I wanted to say. And as from this question, the answer to this will be ketones and carboxylic acids. Right? No, just a second. sorry, it is ketones and sulfoxides. I, I mixed up, okay? So, ketones and sulfoxides are found in higher concentrations in the initial stages of aging, okay? Where ketones, with increase in time, it will first have a higher rate of increase and then it will reach a constant, whereas the sulfoxides will keep on increasing. Okay. And the other components, they are at higher concentrations at the later stages of aging. So the answer to this is ketones and sulfoxides. Next question. The long-term aging residue should be tested within dash hours of performing the test. So this comes under laboratory simulation of aging. So what is the need to do a laboratory simulation of aging? So you cannot wait. So aging happens in two stages, right? One during construction and the other during service. This we call it as short-term aging, and this we call it as long-term aging. Now, this short-term aging is also, so both these types of aging are simulated in the laboratory for the main reason that in order to wait for the bitumen to age as per long-term aging, you would have to actually wait for 7 to 8 years, right? 7 to 8 years to know how this material has aged. And then you have to identify, or you can evaluate the bitumen. But that cannot be the case, right? That can be one of the researches that can be carried out. But if you want to do, say, compare to bitumen as to how they will perform or how they will behave after on aging, okay, after aging. In that case, you simply cannot wait for 7 to 8 years for the bitumen to get aged, right? You have to have an accelerated process in your laboratory to simulate this aging process. Okay, so it is just a relative process, like you can use it only for relative comparison. You can use it only to compare to bitumen, okay, as to how they will get affected on aging, but you cannot relate any results that you get to the field, okay, because the aging that happens in the field is a lot more different because it has additional factors coming into it, because for one reason you have mixed your bitumen with aggregates, okay, that will have a major impact on aging. Some of the lighter fractions could be absorbed onto the aggregates for one kind of bitumen. For the other bitumen, maybe it is not getting absorbed onto the aggregates. So all that plays a critical role when it comes to the actual field. So you cannot use this laboratory simulation to extrapolate what could or how the material could behave in the field. In that case, only to do a relative comparison, right, you can do this laboratory simulation. And I told you there are two types of laboratory simulation. One is short-term aging and the other is long-term aging. Now if you see short-term aging, we do this by a rolling thin film oven. And this long-term aging, we do this using a pressure aging vessel, right? Now this RTFO aged sample you cannot use it after 72 hours, meaning I cannot use it after 72 hours, correct? 3 days. However, this PAV aged sample, they have, so this is mentioned in the code, the respective ASTM code. Whereas the PAV aged sample, I can use it, they have not mentioned any specific time. Okay, you can use it as long as you want, but you have to heat it to 168 degrees Celsius, mix it thoroughly, okay, to get homogenization, and then use it before testing. So that is the condition that they specify in ASTM. So as you see, the long-term aged residue, which will be my PAV aged sample, should be tested within dash hours of performing the test. So there is no specific time to it. Okay. Now moving on to the next question. According to IS 73, the viscosity ratio between short-term aged and unaged binder at 60 degrees Celsius. So if you see the specification table in IS 73, there will be a list of tests, say penetration, softening point, okay, ductility, viscosity at 60, viscosity at 135, okay, flash and fire, yeah, and then these tests are performed on unaged bitumen. Why do I say that they should be performed on unaged bitumen? Because after this, okay, there will be a row which says test to be carried out on RTFO aged bitumen, and in that they will say two values. One is ductility and the other is viscosity ratio. Okay. So what is this? So now our question is about viscosity ratio now, right? So in IS 73, you do not do any tests on PAV aged sample. You will do tests only on RTFO aged and unaged samples. Now this viscosity ratio is nothing but the viscosity of RTFO aged sample to viscosity of unaged sample. Okay, so this ratio should be limited, which means it has to have a maximum value, like it has to be it has to be below a maximum value, and that value is 4. So I'm telling you the answer now. The ratio or the viscosity ratio should have a maximum value of 4. But why? If the ratio is more than 4, it means that your sample is highly susceptible to aging, right? Because your properties have drastically changed on aging, just on short-term aging, right? That is why you are limiting it to a maximum value of 4. Okay. Now moving on to the next question. Steric hardening is observed when bitumen is dashed. Okay. So what do you understand from aging? How to characterize aging besides the the change in the chemical composition on aging, right? The one thing which you could cleanly observe is its increase in stiffness. Okay, from by doing some rheological test or consistency measure, you can easily identify that on aging there is an increase in stiffness. This increase in stiffness when it happens due to aging, okay, or when it happens due to a chemical aging, to be more precise, it is irreversible. And when does this chemical aging occur? The aging that we just saw, the short term aging, long term aging. So this is laboratory simulation, but let me say short term aging, long term aging, they are irreversible processes. Why are they irreversible? Because when you add, sorry, when so how does this aging occur? It occurs due to many factors. Okay, one main factor for short term aging, it is mainly temperature and temperature and presence of oxygen or air. Okay, so the sample undergoes the material undergoes oxidation, because of which the new chemical compounds are formed. Okay, or the chemical composition changes. So in that case, so this happens in short term aging. For long term aging, there are many factors, okay, that um, that influence aging. Many factors, as in it could be sunlight, it could be beta and gamma rays, along with oxygen and temperature. And what all these do is they so these factors can cause a lot of changes, like evaporation of lighter components. Evaporation, I will write volatilization as evaporation of lighter components. Okay. Okay, this is also irreversible, right? Because your components have been evaporated. Then this, it could be oxidation, okay, in with or in the presence or absence of sunlight. Okay, so there are many. There are sorry. Sorry, where is it? Yeah, so there are many factors, and there are many phenomena which happen because as a result of these factors. These phenomena are irreversible phenomena. Okay, so all this short term aging and long term aging are referred to as chemical aging, and they are irreversible phenomena. Now there's something called as reversible aging, and as the name says, they are reversible phenomena. So and there are again two types of reversible phenomena. One is low temperature physical hardening, okay, and the other is steric hardening. So they cannot exactly be called as aging, okay, they are called as hardening. And what actually happens is, when you store bitumen, okay, below its glass transition temperature, okay, it so yeah, so the free volume, so this this is a graph of free volume versus temperature, and this free volume decreases with decrease in temperature, and then it attains a stable value. Now below this glass transition temperature, this is my glass transition curve, below this glass transition temperature, so this curve is the equilibrium state of the material. Now below this glass transition temperature, it actually, the material is not in a mobile state. The mobility of the material, or the molecules in the material, is highly restricted, okay, with this, below this glass transition temperature, but it will try to come to its equilibrium state. So there is a constant reorientation of the molecules below the glass transition temperature. So you know that you should be knowing, or from ma'am's lectures, that the glass transition temperature of bitumen is around minus 20 degrees Celsius, which is identified as low temperature for bitumen. Now, if you go below this glass transition temperature, I told you that the material will be in a constant state of trying to attain its equilibrium state, right? So, if you test bitumen in this state, you will not get the exact properties of bitumen, because they will always be in transient state. They will always be transitioning. Okay? In order to capture the true behavior, let me call it as true behavior of bitumen, okay, within quotes, because you definitely cannot say the true behavior of bitumen, but still the behavior of bitumen without this transient nature, okay, can be obtained when you heat bitumen to a temperature above this glass transition temperature. When you heat it above this glass transition temperature, or take it above this glass transition temperature, then this transient nature is lost, okay, and you will be able to capture the response of the material. This is for a low temperature physical, this is a low temperature physical hardening phenomenon, because it happens at below glass transition temperature. There's one more phenomenon called steric hardening. This need not occur at low temperatures like minus 20, but even at room temperatures, let us say ambient temperatures, okay, of say 25 degrees Celsius. It can be ambient temperatures, okay, where the bitumen is stored at ambient temperatures. you 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 shouldn't expect, or you basically will not be expecting the material to show changes in behavior day by day, right? But actually it will change because of because of this steric hardening, okay, property. Now if you see, again the material is in a transient state here, okay. So if you see the change in properties with time, okay, with increase in storage time, say my modulus will increase, and then it will attain a constant value, okay. Though it, so now you may think that I'm testing the material at, so let us say you're testing material at time t1 here, t1, t2, t3, t4. Now you may think that, okay, you're testing the material at time t1, you're observing one modulus value. You're testing it at time t2, you're observing one modulus value. t3, one modulus value, and t4, after t4 you're able to observe a constant modulus value. Just because you observed a constant modulus value, it doesn't mean that that is the behavior of the material, because it is a completely reversible phenomenon, okay. This has to be removed from material only to only then you will be able to capture again the true behavior of the material. Why? Because say because let us say there are two drums, okay, and one drum you have heated it recently, or okay, you received recently, both same material, okay, same material, okay. For a moment, let us say both have same rheological properties, same everything, okay. But let us say this has been stored for 1 day and this has been stored for 1 week. Though this has achieved a constant material property, say you're testing, say after 1 week, maybe after 1 week, at whatever time you measure the properties, the property G star is expected to be the same. Why? Because after a particular point the steric hardening reaches a asymptotic value, right? But if you try to compare it with this material, it it would have been in time t1. You might be thinking, what is the reason for me to get this huge difference? But you simply cannot wait till it reaches an equilibrium state, because that is actually not the true behavior of the material. So in order to get the true behavior of the material, you have to remove the steric hardening, and removing this is easy because it is a reversible process. And even in ASTM standards, they call a process called annealing, which removes this to remove this steric hardening. So one such method, okay, let me say with respect to a dynamic shear rheometer. So when you test a sample in a dynamic shear rheometer to remove this annealing, they advise you to heat the bitumen, okay, stir it to ensure homogeneity of the sample, and then add it and then pour it into silicon molds, okay. So that also they say that, so even after pouring it in silicon molds, since the volume is very less, since the mass is very less, say how much volume will you or how much, what is the size of the sample in a DSR? It is 8 mm diameter, 2 mm height, or 25 mm diameter and 1 mm height, right? So in that case, the sample is very small. So you should not be testing the sample beyond 4 hours. Okay? After you have heated and poured the sample, again it will start forming a structure, right? Because it is again kept in a constant temperature. Beyond 4 hours you cannot test this sample, and you cannot reheat this. You can maybe reheat the same sample and use it, but you cannot test the sample because it is expected to again have steric hardening. Okay, so in that case, steric hardening is one which occurs at ambient temperatures or ambient constant temperatures. Constant refers to isothermal, right? Iso is same. So isothermal temperatures or ambient temperatures. So if we go back to this question, so steric hardening is observed when bitumen is subjected to temperature less than Tg. No, this is what we saw for low temperature physical hardening. When it is stored at isothermal temperatures, yes. When it is subjected to elevated temperatures, we saw that when it is subjected to elevated temperatures, if it is very high, it undergoes aging, or if it is a temperature greater than 70 degrees Celsius. So if you see, they would have mentioned that if you heat bitumen at temperature greater than 70 degrees Celsius, do some kind of conditioning at a temperature greater than 70 degrees Celsius, it is expected to reverse the steric hardening. So when it is either it causes aging or it is to remove steric hardening, okay, or when it is subjected to repeated loading. No, when you do a repeated loading, you may observe fatigue in the material, but not steric hardening, okay. That is not the answer. So the answer to this is stored at isothermal temperatures. Next question is, aging in bitumen occurs due to what? So here, if you see here, I would have mentioned aging in bitumen occurs due to evaporation of lighter compounds, which we call it as volatilization or loss of volatiles. Is it uptake of oxygen? Yes, because it undergoes, when the bitumen undergoes aging, it undergoes oxidation. So it occurs due to uptake of oxygen. Absorption of lighter fractions by aggregates. So when I explained long-term aging also, I explained that with so when you mix it with aggregates, the lighter fractions get absorbed to aggregates, and so its stiffness will increase, or the material stiffness, the stiffness of the bitumen will increase. So it is due to because of this also. Okay. So the answer to this is all of the above. When you do a laboratory simulation of aging, you will try to simulate only this loss of volatiles and this uptake of oxygen, because you are doing it laboratory simulation, you are doing it only on bitumen, right? So you're not doing it on aggregates, bitumen plus aggregates. That you will do it on aging of bituminous mixtures. But this RTFO aging and PAV aging of binder, we try mostly to focus on loss of volatiles and uptake of oxygen or the oxidation process. Okay, that is why we supply it with air and heat. So when you heat the bitumen, it is expected to lose volatiles, and when you supply oxygen to it, it is expected to undergo oxidation, both of which are results of aging. Correct? Now, so the next question: oxidative aging typically causes dash in stiffness in the case of unmodified bitumen. So this we saw, this I explained here itself. Aging is increase in stiffness. So the answer is an increase in stiffness. Okay. Long-term aging is the aging that occurs from refinery endpoint to laying and compaction in field, from refinery endpoint to mixing in field, from mixing to compaction in field, from laying and compaction to service in field. So I said short-term aging is to simulate the is because of the mixing and compaction. So when mixing, you generally mix it at 165 degree Celsius and compact it at a temperature a little lower than that, like 150 degrees Celsius, right? And when you subject the material to such elevated temperatures, it undergoes aging. And if you see the change in the chemical properties or chemical composition of bitumen, okay, when it is heated during mixing and compaction is drastic, because the temperature it has been subjected to is humongous, right, compared to the service temperature. So when it undergoes long-term aging, which is during the service, okay, after compaction, okay, that the increase in the aging index, or let me call it as aging index. Aging index is some consistency measure, could be viscosity at time t divided by viscosity at time 0, like initial state, okay, before mixing. So so this long-term aging, it happens from laying and compactions to service. So long-term aging is always refers to the aging that occurs during the pavement service. The test temperature for simulating long-term aging using a pressure aging vessel based on standard procedures. So let us see the procedure for RTFO first. For RTFO, the bitumen is heated to 163 degrees Celsius, or the temperature in the RTFO oven, okay, it's not heated to, in the RTFO oven is maintained at 163 degrees Celsius for 85 minutes. Okay. Whereas for a PAV, so here also you will be supplying it with air of this flow rate, 4 liters per minute or 4000 ml per minute. So you do it for a particular duration, you supply it with air and you heat the bitumen. Okay, all this to replicate the short-term aging or to simulate the short-term aging, so that with at elevated temperatures, so it shows a loss in volatiles, and in the presence of oxygen it undergoes oxidation. So in PAV also you require an increased temperature, an increased duration, because it is long-term aging, it is used to simulate long-term aging, and an increased pressure. Why is it increased pressure? So here what will you do for RTFO? You pour the sample into glass bottles and you will keep on rotating these bottles, okay, such that the air gets evenly so the air gets access to all the sample in the bottles, okay, for even oxidation, right? If not, what will happen? Only the surface will undergo oxidation and it will form a kind of a skin, okay. So in that case, in PAV, this will not be rotated. So um, one important thing that you have to notice is an RTFO-H sample will be used for PAV aging, and this, unlike RTFO bottles, it will be placed stationary in the pressure aging vessel. Now not only this top portion has to be oxidized, the entire, though the film thickness is as per what they say, the entire layer of bitumen, the entire thickness has to be oxidized, right? And this can be done by forcing or subjecting it to a high pressure so that air molecules or oxygen molecules get diffused into the layers and then take part and oxidation takes place, okay. So you have to provide these three, okay. Now this duration, it is for 20 hours, okay. This pressure is 2.1 MPa. Why? Because I told you it has to be very high so that the oxygen can diffuse through the layers. Duration 20 hours because it is obviously a long term aging, it has to be a longer duration, obviously. And temperature, now this has to be a representative of the field, right? So what they made is, so this is to this is to simulate the mixing and compaction temperature. So it is done mostly at 165 degrees Celsius, right? Even in the code they would have mentioned that if you do mixing and compaction temperature compaction at any temperature other than 150 degrees Celsius, you cannot use this procedure. But still we are using it for modified bitumen, though its mixing temperature is close to 180 degrees Celsius. Now leaving all that, coming to pressure aging vessel. So here the temperature has to be representative of the field, right? So what they did is 90 degrees for cold climates, 100 for normal climates, and 110 degrees Celsius for hot regions, okay. So this is how they wanted to set the temperature for pressure aging vessel. Now if you do so if you test two bitumen, okay, at two different temperatures, when you subject two bitumen to pressure aging vessel at to long term aging at two different temperatures, you may not get the same output, okay? Maybe same rheological properties, like the change in the rheological properties need not be the same if you do it at different temperatures. The same bitumen if you do it at different temperatures, okay. So that has to be noted. So if you see here, the temperature, is it constant for all the cases? No. That is for RTFO. Depends on the climatic condition of the location? Yes, because we saw 90, 100 and 110 depending on whether it is a cold place or a hot place or a normal place, okay. Depends on the age of the pavement to be simulated? No. All the PAV aging is for is to simulate bitumen for 7 to 8 years of aging, so it does not depend, you cannot simply increase the duration to represent an increased age of the pavement, okay. So that cannot be done. It depends on the grade of the binder? No. Okay. So moving on to the next question, which is dash functionality is formed in bitumen only on aging. Okay. So when I explained the 4 functional groups which are formed on aging, which is ketones, sulfoxides, anhydrase and carboxylic acid, I said that carboxylic acid is present both before and after aging. So it can be present both before and after aging as well. So it is not formed only on aging. So this is not the answer. Pyrrolic and 2-quinolones are present in bitumen even before aging. So they are not formed in bitumen on aging. So ketone is the only functionality that is amongst this which is formed only on aging. Though carboxylic acid is formed on aging, It is present. It is not found only on aging because it is already present on aging. It can already be present in bitumen as well. Okay. So the answer to this is ketone. Two bitumen samples from same source are aged at 100 and 120 degrees Celsius for 3 days. The magnitude of oxidation products formed will be what? So here it talks about the influence of temperature on aging. And as I said, why do they always associate a model to a material? In order to understand or in order to associate the change or the behavior of the material, okay, with the model. Okay, if they are able to find some relations to it, then maybe they can go ahead with the model, right? It helps to understand the material better. So in that case, to understand the influence of temperature on aging also, they use this colloidal model, right? We saw that the colloidal model has a core, asphaltene core, surrounded by lighter molecular weight fractions. With increase in distance, the molecular weight decreases, right? So this colloidal model, with decrease in temperature, normal, without aging, with decrease in temperature, it exists in something called as gel state, where all the micelles will be agglomerated, okay, and they will exist in a gel state, or kind of an, we can say that its modulus will be, so its viscosity will be very high, and it is expected, or it can be considered as an elastic state, okay. And at high temperatures it exists in a solid state where the micelles will be dispersed, okay. This is solid state at high temperatures. So when you subject the material to high temperatures, okay, when these micelles are dispersed, okay, they have higher contact points with oxygen, and so the oxidation products that are formed in this solid state is more. So when you subject the material to higher temperatures, the aging products that are formed will be more, okay. Whereas in the case of gel state, all these are protected by the outermost layer, and only this layer is prone to oxidation due to the changes due to aging, okay. So in that case, the oxidation products formed when the temperature is less will be less. So if your so here they mentioned that the bitumen samples are from the same source, right? And they are aged at 100 and 120 degrees Celsius for 3 days. So the oxidation products formed will be more when it is aged at 120 degrees Celsius, because they have higher contact points for oxidation. Okay. So higher for samples aged at 100 degrees Celsius? No. Will be identical? No. Will be higher for samples aged at 120 degrees Celsius? Yes. Okay. In the rolling thin film oven test, the sample is coated on a glass jar. So when I explained RTFO and PAV itself, I said that RTFO keeps on rotating because it has to avoid this skin formation, right? Wherein only the topmost layer undergoes oxidation, right? Okay. So it is not for ease of placement in the oven, it is not for ease of handling, it is not to minimize the sample requirement. Okay. So moving on to the next question. For simulation of bituminous mixes in the laboratory, select correct answer from the following that describes the state of mix. So long we saw laboratory simulation of bitumen, where we did RTFO for short-term aging and PAV for long-term aging, right? In the case of mixes, okay, you will do an aging after you mix, okay, to simulate the aging that is undergone by uh, during mixing in the field. Okay, so you mix the sample, okay, aggregates and bitumen, and you will age the sample in an oven for 2 hours. Why ma'am would have said 4 hours? Because it is as per the old code. Now it is just 2 hours, okay, in the loose state. Why loose state? Because you've just mixed the sample, okay, and once you compact it, right, once you compact it, so this is for short term aging. And I'm not sure whether it is 2 hours or 4 hours. I'll just go as per ma'am, okay, which is 4 hours. But um, I, I guess that the code has been revised to 2 hours. I will check and let you know in the next session. Okay. So, so loose state, which to represent the short term aging, and once you compact it, okay, you will long term age the mix. Why? Because this long term aging happens after compacting, when the material, when the bituminous mixture is in service, right? So at that time it would have already been compacted, whereas the short term aging occurs on mixing. So there you will age the loose mix in the loose state. Okay, so loose mix for both aging conditions, no. Compacted for both aging conditions, no. Loose mix for short term aging, and compacted specimen for long term aging. Okay, it is not this also. Okay, now moving on to the next question. Fraction in bitumen which will not undergo any change due to aging. So when they try to study aging, they try to study the change in the elemental composition on aging, change in the functionalities on aging, on aging, uh, fractions, the SARA fractions on aging, okay, and they also try to relate all of this with the physical uh, behavior of bitumen also. So now the SARA fractions, what they were able to see is asphaltens was the one which to undergo the greatest change, the highest change in changed during aging. These two were able to they were able to observe light changes, okay, lesser changes, and it also depended on the type of bitumen, whereas saturates did not undergo any change on aging. So the answer to this is saturates. Okay. Which among the following mechanism of aging occurs only on the surface? Okay. If you see, volatilization, so oxidation occurs only on the surface, we all saw, because only when you keep a bitumen and when you subject it to aging, the topmost surface will be oxidized, okay, unless and until you force air into it, only the topmost surface will be oxidized. Also, even for in the case of mix, it is like that, okay. The topmost surface will be oxidized because of the influence of temperature and oxygen, okay, because of the access of oxygen to the topmost surface compared to the lower regions. Volatilization, it happens throughout, like even in the depth, not only on the surface. Thixotropy is not a mechanism of aging, so I don't think it even comes here. Adsorption by solid, you mix bitumen, right? So in that case, it does not happen on the surface, okay, unlike oxidation. Short-term aging is characterized by what? Short-term aging is characterized by, so remember RTFO and PAV procedures that we saw? Here we subjected it to 163 degrees Celsius, here 90 to 110 degrees Celsius, so higher temperatures. Here we subjected it for 80 minutes, here for 20 hours. So it is characterized by high temperature and shorter duration. Okay. This is this is not only for laboratory but also for mixing and compaction, because mixing and compaction occurs for a very short duration, right? And also it occurs for 165 degrees Celsius, at 165 degrees Celsius, which is very high compared to the service temperature of say 50 or 55 or 60 as high temperature, pavement high temperatures. Okay, so it is very less compared to the long term aging which happens in the field, and also the duration of long term aging is very long, right? Because it happens during the service, right? So it happens, it is characterized by higher temperatures and shorter duration. The increase in aging index is highest during mixing. We saw a few minutes back, right, that during mixing the increase in aging index is the highest, uh, and then it reaches, and then it gradually increases. Okay, so yeah, so that's it for this week. um, okay, so if you have any doubts, please contact me. Please post a comment below the YouTube video. Okay. Yeah. So yeah. So let me end this class. Okay. Thank you all.